This video is part on the review on sequences and series necessary for us to understand some concepts in real analysis. For this time, we are going to prove that the limit of a rational expression 1 over n as n approaches to infinity is equal to 0 using the definition of a limit of a sequence. So for us to be able to do this, we need to structure our proof using a definition. It said that there is a limit, or our sequence is converging to a limit which is probably identified as x if for every epsilon greater than 0 there exists a natural number such that for all n greater that natural number, let's say k, it satisfies this expression. Per definition, we need to satisfy this expression minus our sequence minus the limit is less than that said epsilon. So we can structure our proof for this given item here by following the said statement here. So for us to be guided, this is a separate portion. Our sequence is 1 over n minus the limit of 0 less than epsilon. So we have the absolute value of 1 over n is less than epsilon. In short, if we could come up with in our proof into this form, then we have verified that the limit of the said sequence 1 over n as n approaches to infinity is really equal to 0. This is a helpful expression, and then that's our target if we could reach into that. This is how the proof will come out. Let's start by, of course, letting the epsilon greater than 0, so that epsilon will come out later. And of course, part of the definition for the limit is that for every epsilon greater than 0. With this, we can also say, okay, following its reciprocal, 1 over epsilon is still greater than 0 as you took the reciprocal of your epsilon. No matter how small it is, its reciprocal is still greater than 0. Now, part of a definition for the limit of a sequence is that for every epsilon greater than 0, there exists a natural number k, such that for all n greater than that set k, it satisfies, again, this statement here. Where do we get a natural number k? Let's have this. By a certain property, also known as Archimedean property, or others will call it Archimedean principle, it states that for every real number that you can think of, there exists a natural number greater than or equal to that. So whatever real number that you can think of or you can mention, there is always a natural number, n in this case, or k, as we're going to use it later, always greater than or equal to that real number that you're thinking of. With this, since we have established here, or part of the proof for the limit of a sequence is that for every epsilon greater than 0, there is this natural number k, right? So we can introduce here, there exists k. Let's say that k is element, or that's a natural number, such that, okay, it follows this form, that k is still greater than 1 over epsilon. Or just for the structure of the Archimedean property, you could also state that 1 over epsilon is less than k. Right? So that's by Archimedean principle. Hence, we can form here a certain expression in terms of epsilon, because take note that our goal here is where an epsilon is greater than 1 over n. If we could reach this, then we have proven that our limit is true. So hence, okay, by the process of cross multiplication, or multiplying both sides by epsilon and dividing both sides by k, you will have 1 over k is less than epsilon. So you can see that there is already an epsilon here. Now further, we're going to look into other processes or involved in this proof that we could structure this. Okay, so with this here, then part of the definition for n greater than or equal to k. This is the definition of the limit, because for every epsilon greater than 0, there exists natural number k rather, that such that for all n greater than k, it would satisfy this. So that's our goal here. We have, okay, let me change the color of my pen here. Okay. we have taking the reciprocal of n. Okay, take the reciprocal of n. So 1 over n. And then 1 over k here. Take note that when we take the reciprocal of a number, the sign of the inequality changes. Okay, the sign of inequality changes. So we have this form here. But take note, earlier we have established this. Since 1 over k is less than epsilon, you have here 1 over n is less than or equal to 1 over k. That's less than epsilon. Removing this middle here, you will have this form. 1 over n is less than epsilon. So we have arrived into this criteria in order for us to say that our limit of the sequence 1 over n converges to 0, the limit that we have on part of our proof. Okay, so now that we have established this, what we just need to do is the final statement. Consequently, okay, if n is greater than or equal to k, then, okay, we have here the limit or the absolute value of 1 over n. This form here, we could use that. 1 over n minus 0. This, again, the sequence, that's the limit, right? Take note of that. That's part of our item earlier. Which is equal to 1 over n is less than epsilon. Okay? So, cutting the middleman, we can establish here that the absolute value of 1 over n is equal to 0, or minus 0 rather, is less than epsilon. This already satisfies the definition of our limit. Therefore, okay, you can write now the limit of the sequence 1 over n as n approaches to infinity is equal to 0. This is the proof for the given limit. Take note, again, a short review. We were able to look into this first because it would guide us what to be our target. Once we were able to get this, now we move to the proof, looking into the properties that we need to examine. We introduce the Archimedean property because that's applicable here as we establish a certain natural number k, which is greater than 1 over epsilon, a real number. Then we were able to get a certain expression for k, and then for the epsilon itself. Then looking into the further statements of our definitions part of the proof, we have this statement here, which we're able to get the reciprocal into this. Looking into the relationships of previous already formed relationships, we're able to come up with this and reach our intended target given to us by this preliminary computation. And that we have established that this part of our definition, later on we're able to come up with the final form that the limit of, again, the said sequence 1 over n as n approaches infinity is equal to 0. So please bear with this and use this as part of your future proof. Thank you very much for watching.